IP version 6, that is IPv6, is a new version of the Internet Protocol and is designed as the successor to IP version 4, that is IPv4. This protocol is defined by RFC 791. Now let us brief categories for the changes from IPv4 to IPv6. 1. Expanded addressing capabilities. IPv6 increases the IP address size from 32 bits to 128 bits to support more levels of addressing hierarchy, a much greater number of addressable nodes, and simpler auto-configuration of addresses. The scalability of multicast routing is improved by adding a scope field to multicast addresses, and new type of addresses called an anycast address is defined and is used to send a packet to any one of a group of nodes. Second, header format simplification. Some IPv4 header fields have been dropped and made optional to reduce the common case processing cost of packet handling and to limit the bandwidth cost of the IPv6 header. Third, improved support for extensions and options. Changes in the way IP header options are encoded allows for more efficient forwarding, less stringent limits on the length of options, and greater flexibility for introducing new options in the future. Fourth is flow labeling capability. A new capability is added to enable the labeling of packets belonging to particular traffic flows for which the sender requests special handling, such as non-default quality of service or real-time service. Point 5 is authentication and privacy capabilities. Extensions to support authentication, data integrity, and data confidentiality are specified for IPv6. Figure shows IPv6 header format. Let us brief IPv6 header format components. Version. Version is 4-bit Internet Protocol version number and is equal to 6. Traffic class. Traffic class is 8-bit traffic class field. Flow label and is 20-bit flow label. Payload length. Payload length is 16-bit unsigned integer. Length of the IPv6 payload, that is the rest of the packet following this IPv6 header in octets. Next header. Next header is 8-bit selector and identifies the type of header immediately following the IPv6 header and uses the same values as IPv4 protocol field. Hop limit. Hop limit is 8-bit unsigned integer and is decremented by 1 by each node that forwards the packet. The packet is discarded if hop limit is decremented to 0. Source address. Source address is 128-bit address of the originator of the packet. Destination address. Destination address is 128-bit address of the intended recipient of the packet. Now let us look at IPv6 extension headers. In IPv6, optional internet layer information is encoded in separate header that may be placed between the IPv6 header and the upper layer header in a packet. There are a small number of such extension headers, each identified by a distinct next header value. Extension header order. When more than one extension header is used in the same packet, it is recommended that those headers appear in the order defined as follows. First, IPv6 header, then hop by hop option header, then destination options header, then routing header, then fragment header, then authentication header, then encapsulating security payload header, then destination option header, and at last upper layer header. Each extension header should occur at most once, except for the destination options header, which should occur at most twice, that is, once before routing header and once before the upper layer header. If the upper layer header is another IPv6 header, that is in the case of IPv6 being tunneled over or encapsulated in IPv6, it may be followed by its own extension headers, which are separately subject to the same ordering recommendations. If and when other extension headers are defined, their ordering constraints relative to the above listed headers must be specified. IPv6 nodes must accept and attempt to process extension headers in any order and occurring any number of times in the same packet, except for the hop by hop option header, which is restricted to appear immediately after an IPv6 header only. Nonetheless, it is strongly advised that sources of IPv6 packets adhere to the above recommended order until and unless subsequent specifications revise that recommendation. Point options. Two of the currently defined extension headers are 1. Hop by hop options header and second destination options header, which may carry a variable number of type length value, that is TLV, encoded as options. The sequence of options within a header must be processed strictly in the order they appear in the header. A receiver must not, for example, scan through the header looking for a particular kind of option and process that option prior to processing all preceding ones. Hop by hop options header. The hop by hop options header is used to carry optional information that must be examined by every node along a packet's delivery path. The hop by hop options header is identified by the next header value of 0 in the IPv6 header. Routing header. The routing header is used by an IPv6 source to list one or more intermediate nodes to be visited on the way to a packet's destination. Fragment header. The fragment header is used by an IPv6 source to send a packet larger than would fit in the path MTU to its destination. Destination options header. The destination options header is used to carry optional information that need be examined only by a packet's destination nodes. The destination options header is defined by the next header value of 60 in the immediately preceding header. No next header. The value 59 in the next header field of an IPv6 header or any extension header indicates that there is nothing following that header. If the payload length field of the IPv6 header indicates the presence of octets past the end of a header whose next header field contains 59, those octets must be ignored and passed on unchanged if the packet is forwarded. Packet size. IPv6 requires that every link in the internet have an MTU of 1280 octets or greater. On any link that cannot convey a 1280 octet packet in one piece, link-specific fragmentation and reassembly must be provided at a layer below IPv6. Flow labels. The 20-bit flow label field in the IPv6 header may be used by a source to label sequences of packets for which it requests special handling by the IPv6 routers, such as non-default quality of service or real-time service. Improvement for this aspect is going on. Hosts or routers that do not support the function of the flow label field are required to set the field to 0 when originating a packet and pass the field on unchanged when forwarding a packet and ignore the field when receiving a packet. Traffic classes. The 8-bit traffic class field in the IPv6 header is available for use by originating nodes and or forwarding routers to identify and distinguish between different classes or priorities of IPv6 packets. Upper layer protocol issues. 1. Upper layer checksums. Any transport or other upper layer protocol that includes the addresses from the IP header in its checksum computation must be modified for use over IPv6 to include the 128-bit IPv6 addresses instead of 32-bit IPv4 addresses. IPv6 version of ICMP, that is ICMP v6, includes the above pseudo-header in its checksum computation. This is a change from the IPv4 version of ICMP, which does not include a pseudo-header in its checksum. The reason for the change is to protect ICMP from misdelivery or corruption of those fields of the IPv6 header on which it depends, which, unlike IPv4, are not covered by an internet layer checksum. The next header field in the pseudo header of ICMP contains the value 58, which defines the IPv6 version of ICMP. Maximum packet lifetime. Unlike IPv4, IPv6 nodes are not required to enforce maximum packet lifetime. That is the reason the IPv4 time to live field was renamed as hop limit in IPv6. In practice, very few, if any, IPv4 implementations conform to the requirement that they limit packet lifetime. So, this is not a change in practice. Any upper layer protocol that relies on the internet layer, whether IPv4 or IPv6, to limit packet lifetime ought to be upgraded to provide its own mechanisms for detecting and discarding obsolete packets. Maximum upper layer payload size. When computing the maximum payload size available for upper layer data, an upper layer protocol must take into account the larger size of the IPv6 header relative to the IPv4 header. Responding to packets carrying routing headers. When an upper layer protocol sends one or more packets in response to a received packet that included a routing header, the response packet or packets must not include a routing header that was automatically delivered by reversing the received routing header unless the integrity and authenticity of the received source address and routing header have been verified. For example, via the use of an authentication header in the received packet.